Alright, we're going to bite off quite a bit to chew tonight. We're going to cover a variety of topics within the chapter of differential equations. And first of all, we just want to establish what a differential equation is. It's an equation in terms of the derivatives of a function. Notice that was a plural derivative, so it could be a function that's defined in terms of both, the original function is first, second, third, fourth, fifth derivative, etc., etc. Kind of a crazy example to set the tone is 3y double prime cosine x plus 5y prime e to the x equals 6y or something like that, And here's the deal. The solution to this equation is no longer a number, but the solution is a function itself. A function such that, it could be like if function f of x was a solution, we could plug the function in for y, his f prime in for y prime, f double prime into this guy. Now this particular one that I happen to just create off the top of my head is what we call a second degree Diffy Q. And that's self-explanatory, I think, because the biggest derivative in this equation is the second derivative. Within this class, we're going to limit ourselves to just first degree Diffy Q, and most of the time, they're going to be separable Diffy Qs. And if they're not separable, then we'll take a look at some other techniques, whether it's slope fields or Euler's method, that'll help us kind of approximate the solution. But as far as getting the exact solution analytically, we're going to rely on our method called separation of variables. So I figured we'd start off with a nice warm-up here, and then want to find the particular solution. Okay, so it's going to be the general solution plus some additional work beyond that for this Diffy Q. Now, just a nice little subtle trick here. I want to take this radical y that was on the left side, and I just want to add him to the other side. So we've got x radical y plus radical y on the right side. And we don't do this often enough, but I want to take out a GCF. We haven't used this technique too much with separating the variables. And now we could divide the radical y over to the left, and we've got the quantity x plus 1 times dx on the right. So at this moment right now, we're pretty happy because we successfully separated the variables, and we've at least got a chance of solving this one. As I get ready to integrate, I'm going to take one more baby step, and I'm going to rewrite the left side as y to the negative 1/2 just to help us visualize this power rule that's coming down the road. And what I'm going to do here is I integrate. We are going to add 1 to that exponent, and we're going to multiply by the reciprocal of that new exponent. And we've got equal to 1/2 x squared plus x plus c. And right here is where we have the general solution. Okay, so typically on a free response question, if I stop right here, I've earned 3 points, 1 for separating the variables, 1 for integrating the left side, and 1 for integrating the right side. And that's typically how the rubric's broken down. Now you have choices. Do you want to go find the value of c now, solve for y later, or vice versa? Do you want to solve for y now and then get the value of c later? For this particular one, I'm going to choose to find the value of c now. And for no particular reason, otherwise than I just felt like it, I guess. I'm going to substitute a 9 for y and a 4 for x. See, 9 for y, 4 for x. 9 for y, 4 for x. Okay, so we've got 2 times radical 9 equals 1/2 of 4 squared plus 4 plus c. Okay, so we've got 6 equals, 8 plus 4 is 12. Subtract the 12. I got negative 6 as my c value. So all I'm going to do is I have to plug that in exactly where my c was when I started subbing. Okay, that's gotten us into trouble a few times where we find the c value and then we go back up here and we start solving for y right away, and we think that we could then plug the negative 6 into the c later. Okay, it has to happen right now. And so we've got 2 radical y equals 1/2 x squared plus x minus 6. And all we're going to do is we're going to divide everybody by 2 and then square both sides. Nothing real profound here yet. So hopefully you're feeling pretty good. 1/4 x squared plus 1/2 x minus 12. And y equals that entire quantity squared. I almost wish it was just the opposite. I wish we were taking the square root of both sides. Just recall, if you are taking the square root of both sides, you end up getting a plus or minus on the right side, and then you have to make a decision whether you want the positive or the negative root based on the initial condition and whether the original y value is positive or negative. And you have to choose one over the other so that it becomes a function. One of the most profound and practical applications we see in our entire course is differential equations with respect to exponential growth and decay. And this fancy Diffy Q we have here at the top, as we interpret that, it's simply saying this equation states that variable p increases at a rate directly proportional to the variable itself. Let's see, directly proportional. Now, the only difference between what we had in our notes earlier is I usually don't use the letter R. I would usually say K for directly proportional. So I'm thinking the derivative of capital P with respect to T is equal to lowercase k times capital P. So that's how I would typically write an exponential growth or decay problem. And sometimes that's a lot of jargon, and it doesn't quite sit in. But I want you to think of a real life example. Maybe we're talking about bacteria population, and we're saying that as bacteria population increases, there are more individuals capable of reproduction, so that the rate of increase now also increases. And when I saw that example, it just made a lot more sense and kind of, brought this particular Diffy Q to life for me. So I want to talk about solving this popular Diffy Q and being able to skip those steps and going right to the solution in the future. So if I take that very popular Diffy Q and I separate the variables, I'm going to get dp over p equals k times dt. And the natural log of the absolute value of p is equal to k times t plus c as we integrate. We're going to take the base e of both sides, and we get e to the kt plus c power. And that's where we're going to kind of decompose, and we're going to say e to the kt times e to the c. Make sure that a plus sign in the exponent becomes a multiplication sign when you decompose there. And therefore p is equal to, and e to the c is just a new constant. We're going to use a capital C to represent a different number, e to the kt. So this is the solution to this very popular Diffy Q, and you're more than welcome on a test to just skip from the Diffy Q down to the solution. And if you feel comfortable, let's skip these steps in here. So here's a great problem to try to challenge yourself with. It's definitely going to be calculator active, and I encourage you to go grab yours, hit the pause button, walk out to your car, pull it out, book bag, car, upstairs, wherever, go get your calculator, come on back, try to solve this one on your own, and of course make sure you store any intermediate crazy answers and then round your final answer to 3 decimal places. Okay, they said the population of the bacteria contains 2,400 cells 3 hours ago in the past, and it's now currently grown up to 5,200 cells. Now, assuming that the rate of growth, and I'm going to take that right there, and I'm just going to instantly say dp dt, I'm going to let p represent the population, means equals, proportional means k, to the number present, current population, right? And the solution to that Diffy Q is going to be p equals c e to the kt, where c represents, and here's a tidbit, if you didn't know this already, C is the population when t equals 0. Now there is a little bit of a stickler here. They're saying from now. So they're saying currently, right now, at t equals 0, there's 5,200. And then 3 hours ago, that would mean t equals -3, the population was 24. So we usually don't work with negative time, but t equals 0 kind of represents a starting point, and then negative time represents something in the past, positive time represents something in the future. And I believe one of the classes kind of brought this up not too long ago, and we had an interesting mini discussion about it. So anyway, knowing this number happens at t equals 0, I can instantly substitute it in for c. So we've got my 5,200 e to the kt, but k is also an unknown constant. So now I'm going to use my second initial condition and say 2,400 equals 5,200 e to the -3k, and I'm going to try to solve for k, and that'll be kind of my halfway point. And here's some hardcore algebra. We're going to divide the 5,200 over, and I'm going to kill some zeros, and then we're going to take the natural log of both sides, So we've got the natural log of 24 divided by 52. Throw in your calculator. Then divide that by -3. And I ended up getting like 0.2577 for my k. And I stored that in alpha a or some other letter that you like. So now my particular solution is P equals 5200 e to the alpha AT. And they want to know how long is it going to take before the cell population grows to 10,000. So I'm going to substitute that for P and then solve for T. So again, I'm actually now going to repeat a lot of the same steps you just witnessed not too long ago. We're going to divide that 5200 over. We're going to take the natural log of that. It's like 100 divided by 52. And let's see. Then all I got to do is divide that alpha A over. And when I threw that in my calculator, I got about 2.537 hours. I hope your answer agrees with mine. If it doesn't, we can solve that discrepancy tomorrow, but that should be the answer. This is the one that we love, and this is the big bear for the BC students. It's logistic growth. And basically, logistic growth says that the rate of change, let's see here, the rate of change of quantity P, I like to use P for population, is directly proportional to both, and I want to emphasize both of these two following things, both itself P and its remaining room for growth. Now, what does that mean, its remaining room for growth? What we do is we take the carrying capacity and we subtract the current population, and it tells me how much room it still has for growth. So what does this look like as a Diffy Q? We say the rate of change of P is directly proportional to itself and usually means multiplication, its room for growth. Now, when you look at that rascal, M represents the carrying capacity. And that just means there are a lot of times in the real life where you do experience exponential growth, but then because of other environmental factors, it's impossible to sustain that growth. And so it begins to taper off and reaches some kind of invisible ceiling, so to speak. So now you've got the Diffy Q here, and we never solved this one in class, okay? At least analytically anyway. But we did take a look at the solution graphically. All right, and it's important here, I'm not graphing the Diffy Q, I'm graphing his solution. In his solution, assuming that his initial condition was less than the carrying capacity, so we'll say M's up here, that's the invisible glass ceiling it has. The graph starts off exponentially. Halfway up, it experiences a point of inflection and tapers off. All right. Now, if for some weird reason there are moments where the initial condition is greater than the carrying capacity, and all we're going to do is it's going to decrease and become asymptotic to that carrying capacity, never go below it. So those are your two potential solutions. The second one there in the light blue is not nearly as exciting. Okay, so let's say that P is the solution function. All right, here's the kicker. What is the limit as t approaches infinity of function P? Okay, well, function P is approaching a height of m. Now twist that around a little bit. What's the limit as t approaches infinity for P prime, his derivative? Well, of course, the slopes are approaching 0. So those are two very famous limit questions I'd like to throw at you. The other question I'd like to throw at you is, at what moment is the solution curve growing the fastest? Of course, that green graph is growing. When is it growing the fastest? Well, at its steepest moment, and that's going to occur right there at the point of inflection, and the point of inflection is always half of the carrying capacity. Then what's weird is that's in terms of, and I don't want to use y, let's use p, the independent variable. And that's kind of unusual. Normally we describe points of inflection in terms of x, but in this time we're describing it in terms of p or y, the dependent variable. One other note there, if you go back and look at the general form of the Diffy Q, it's very important to notice that there are no independent variables in this Diffy Q here. As you look at the general form of that Diffy Q, everything's in terms of p, p, p. There are no x's, and p is, of course, the dependent variable, just like y is. All right, here's a good practice one for us. It says the rate of growth of a certain deer population is given by the differential equation. Whoops, got to get the pen here. Go. All right, dp dt equals p over 50 times the quantity 700 minus p over 3. Okay, where p is the number of deer after t days have elapsed or gone by. So the question becomes, what is the maximum number of deer that the forest can sustain? And that is basically your carrying capacity. Now the temptation is to look at this, say, yes, I've got independent variables in all of the right places. This is logistic, and therefore this number is my carrying capacity. Well, that would be a big mistake, and that is exactly the bear trap they're trying to lure you into on the AP exam. What we need to do is we need to make sure that there are no other coefficients on this term. So what I need to do is I need to factor out a 1/3. And we're going to rewrite the Diffy Q as dp dt. If I factor out the 1/3, I now have p over 150, and 700 divided by 1/3 is actually 2100. And so basically, when you pull out a 1/3, you're multiplying by 3, essentially here. Oops, p's over nothing now except 1. And I did not mean to put that there, I just meant to put p, but yeah, let's try that. Okay, so now we can say that the carrying capacity is 2100, and that's the maximum number of deer that this particular forest can sustain. Another popular question is, at what moment was the deer population growing the fastest? And we would say it's growing the fastest at the moment when the population was, let's say, 1,050. That would be exactly half of the maximum capacity. So, and that's a good example to kind of just get you warmed up and review some basics. So I hope you feel good about Diffy Qs. I hope you feel good about both exponential growth and the logistic growth Diffy Qs. In our next video, we'll take a look at some alternative ways of finding solutions, particularly analyzing slope fields, interpreting them, and also using and implementing Euler's method. So we'll see you later.